Hello, everybody. This is our presentation on one program to rule the intersection and simplifying development of distributed time-sensitive applications. I am Reese Grimsley.
I'm Edward Ander.
I'm Ian McCormick.
I'm Ihu.
And our faculty advisor is Bob Iannucci.
As autonomous vehicles have become widely adopted, it's been proposed to create what are called smart intersections, in which vehicles are precisely scheduled to drive through an intersection at high speed in close proximity to one another in order to increase the throughput over a conventional intersection. However, this is a very hard problem, as the error margins are small, requiring precise timing in a highly distributed environment. Any deviation, even slight, could cause catastrophe. We have developed a pair of 1/10 scale CAVs, or connected autonomous vehicle replicas, using RC cars to simulate and test an intersection safely using Jetson Nanos as the compute platform. These cars have an onboard LiDAR to localize themselves and detect obstacles, as well as a camera running a YOLO V4 CNN at 8 Hz to detect obstacles. All detection, planning, and actuation calculation is done on board until they reach the intersection transmission line, at which point the roadside unit takes over control while the cars are driving through the intersection. The roadside unit, or RSU, receives all the locally fused detections from the vehicles and makes a global data fusion, and then calculates trajectories to send the cars through the intersection. The cars then execute those trajectories as they pass through the intersection. There are many things that are hard about developing such an application, namely synchronizing inputs across vehicles so that sensor fusion is useful, explicitly creating communication, setting up deadlines and timeouts, synchronization, and communication between processes, and more.
To support the kind of time-sensitive applications we just described and address the challenges we encountered, we took a systematic approach and built a system framework that follows the following design principles. First, our framework should be compatible with most of the existing applications. We introduced TTPython, a programming language based on Python 3 to support time-based programming. Second, we want to simplify time management at user level. We introduce mechanisms that abstract the complexity of synchronization at deadline checking. Third, our system should provide a way to handle and recover from failure, especially timing failure. We introduce the idea of Plan B that supports alternative actions. Lastly, we want to hide the complexity of handling network communication in distributed setting by introducing a generic network interface. We will go through each of these points in the presentation. Let me first introduce TTPython, a system-level programming language for distributed, time-sensitive systems. With the idea of writing a single program to rule the intersection rather than a set of separate programs for each device, our objective is to simplify the way distributed applications can be written. TTPython is one such programming language that uses a data flow model with built-in abstractions for timing and communication. The programmer first writes a single TTPython program for the application. The program is compiled into a data flow graph where each arc represents communication and each node is scheduling quanta representing a functional component, which will be introduced later. This graph can be mapped to the system as seen fit. For the example shown on the slide, the smart intersection application is partitioned into 3 parts to be mapped to CAV, RSU, and IS separately, based on communication requirements between SQs. One important idea with data flow decomposition is scheduling quanta. It is a building block of the data flow with useful abstractions that handle synchronization, computation, and data forwarding. The goal of this abstraction is to enable programmers to express timing concepts from the perspective of what to do with time rather than how to do it. The programmer only writes the computation part, which specifies how to process data, and leaves the handling of timing and communication to the system. When inputs arrive, the SQ first synchronize input based on time. Those synchronized input then enter the computation block and the computation runs to completion once enabled. The final stage is data forwarding, where the output data is encapsulated and sent to the network interface for communication.
Within this distributed application, we'll find operations that require sample data from various sources, like different sensors or different devices. To execute those operations, we need to join those values, those streams. We need to synchronize the inputs. And since we're dealing with data from the physical world, that data shares some context based on when they were sampled. Those sampling times probably won't align exactly, but we posit that they don't necessarily need to because that data is valid and useful over some interval of time. So in this way, we can determine which values to synchronize by looking at an interval describing the data's validity with respect to time. And we do know that for inter-device synchronization, this requires the timestamps be derived from synchronized clocks that are accurate to some small percentage of the interval width, where that interval for our application is 125 milliseconds since we're running it at 8 Hertz. And a fundamental requirement for distributed systems is fault tolerance. Failures happen, and we have to be able to recover from those. So in time-sensitive applications, we would consider a significantly delayed response to be a failure. And so if a network or a sensor failure occurs elsewhere in the system, then synchronization may not complete, and we need to move forward with some safe alternative action, a plan B, like slamming on the brakes in our vehicles. And to support these timely alternative actions, we use deadlines at the synchronization stage of the SQ such that we shortcut waiting for inputs. And at that point, we immediately trigger computation with whatever input values are available. And so in this application, we use a deadline on motor actuation for 125 milliseconds after we read an image from the camera, which will cause the CAV to hit the brakes if the roadside unit does not respond with a trajectory or a path within 125 milliseconds of sampling the camera.
As introduced earlier and shown in the diagram here, it's clear that arcs between adjacent SQs can cross device boundaries, requiring network communication. TTPython abstracts over communication, freeing the developer from the challenges of managing the network at an application level. When values travel between SQs, they're passed through a communications layer that packages them with their context and ensures that they're reliably sent to their destination, where they are synchronized at the boundary of the next SQ. This occurs without programmer intervention.
The goal of TTPython was to reduce the load of the programmer by abstracting many tedious and confusing parts of programming complex distributed systems, including communication and timing. And the results show just that. As the original programmer of the Smart Intersection program that we featured earlier as part of a different project, I spent a lot of time programming in TTPython and found it to make programming process significantly easier. As the programmer, I was able to focus less on the nuances of timing and communication and trust that they worked, and instead was able to focus on the operation of the sensor fusion and intersection control algorithms themselves, which in fact resulted in finding some bugs that were missed in the original non-TTPython version of the program. Overall, the results from our instrumentation showed that TTPython was in fact faster than the previous version of the program that was built using a standard communication library and explicit threading. The speedup was notable, at more than 30% on the round-trip delay from when the LiDAR scan was first taken to the actuation. As a result, we hit very few of the 125 millisecond actuation deadlines at a mere 0.7%. The overall latency of TTPython synchronization functions were on the order of about 2 milliseconds, which contributed to a round-trip latency on the critical path of 5 milliseconds on average. This extra overhead is so small, it could almost be considered noise in the application, and we believe that the price is worth paying for the benefits we get from TTPython.
And we've been using the Smart Intersection application as a testbed for TTPython development at many points to continue building on this framework. We'd especially like to test TTPython on other distributed time-sensitive applications and with users who are less familiar with our TickTalk project, such that we can conduct user studies. We also plan to explore this problem of mapping SQs to devices dynamically to optimize SQ placement such that we can improve on system-wide metrics like latency and power consumption for battery-operated devices. And for TTPython, we base our program model on a tag token data flow architecture with new mechanics for dealing with time-sensitive behaviors like sampled inputs and deadlines. We plan to continue down this path to build a more theoretically cohesive model of time-governed data flow. And finally, we'd like to build a community around TTPython. If you're interested, please visit our doc pages, and our code repository is linked here and on our poster. So to wrap up, we've shown that distributed time-sensitive applications are challenging to develop. We've created TTPython to alleviate some of those challenges by using a data flow model in which the nodes or scheduling quanta implicitly handle timing and communication on the developer's behalf. And we've demonstrated this framework on a smart intersection application in which we both simplified the development process and improved overall performance in terms of end-to-end latency by nearly 40 milliseconds. These abstractions don't come for free, but we do find that the overhead is only about 5 milliseconds along the critical path, and that this is a price that we're worth paying for simplifying development of these distributed time-sensitive applications.